Okay, today we have laboratory work, and our work is dedicated to density of states, and it's very good thing that you had heard about it just 30 minutes ago. But today I will tell you very short theory about density of states, very basic theory, and then we will calculate it. So what is density of state? Maybe some of you can say what is state, what is electronic state. Maybe Vladislav, you can just unmute you if you want to say something. If you want, of course. Nobody wants. What is electronic state? You see this beautiful picture with some bricks. It's some
electronic position defined by
quantum number. Okay, so my version, what is the electronic state? This is some space in reciprocal space where electron can be located. Can be because it's a probability space, and we have only some kind of probability that we can find electron exactly in that state. Usually that state are not even numbers, and because because we have some part of probability, and it shows like, okay, some part of electron will be in this electronic state, and we have this reciprocal space. You see these vectors kx, y, z, and we can divide the space into the bricks. So this is small bricks in the wall of this electronic density, and we can calculate its volume. So we can say that let's say this brick is our electronic state. It's some place in the reciprocal space where electron can be found with some probability, and I can calculate its volume. It's very easy. I can calculate it from Heisenberg principle. It will be like 2p divided by L in the power 3, because we are talking about the cube. And then it's very easy mathematics. We can calculate its kinetic energy, p squared divided by 2m. Then we can substitute p as energy, hk, and k and we can take k from here, from this kinetic energy, without some electron. And then I say that all electrons will be located in some sphere with radius of this k. It's connected to Fermi surface. You saw this way of thinking when I told you about Fermi surface, because it was also about free electronic gas, and before you had a lecture also about free electronic gas. So we have some sphere. Inside the sphere, we divide all the space into some bricks, and then we say that all our electrons will be inside the spheres, and they will be in some way substituted. In some way, they will fill all these bricks, all the space. So our space is like sphere with radius k vector. And now also very easy part. I just take this space, this sphere, and divide it by volume of one brick. And I can find, and then I multiply it by 2, because I want each electron with each spin. So I want to allow be here electron with spin up and spin down. That's why I had to multiply by 2 this number of electron states. Here is a number of electron states in 3D. Then we will talk about 2D and 1D and see the difference. So it's 3D. And what interesting thing we can find from it? We can connect it to the energy. Very easy. I can just substitute this k in that formula, and I see that number of electronic states proportional to energy, kinetic energy, in the power of 3 divided by 2, with some coefficient, with some constant. And I can calculate density of the states. How can I do it? I just had to divide it by volume of one by volume of this state, and I'll get the density of states. It is proportional to square E. That's the information you had from previous lecture. So density of states in this simple electronic gas will be proportional to square of energy, and we can more or less build this plot. So we see that a number of states, they will grow to some threshold, to some energy threshold. Will be Fermi energy. So here will be Fermi energy, and all electrons will be under Fermi energy, and up and above Fermi energy we have nothing. I hope it's clear. Then we can do the same for 2D, just for illustration. In 2D, we have not 3D space, but we have some flat space. Here I have these squares like electronic states. I have this circle with radius k, and I have almost the same mathematics. What volume of the state will be? 2p divided by L in the power of 2, because we are working with 2D. And then we work with circle, so its volume will be p k squared, and I can take k from here. And then I do the same to aiming to calculate number of states and density of states. Number of states, I just divide this volume on this and multiply by 2. I get something. Then I get density. So when I get in density, I had to divide it by year, because we are talking about density of states according to energy, and divide by volume, by this unit cell volume, and I'll get constant. So for 2D, for electron gas in 2D, we have constant density of states. And how it will looks like? It will be like steps. So I see at some energy E1, it will be state. Then I have energy E2. I have jump to another step, to another density of states, and so on. And here I showed the 3D plot. So here is 2D, the steps, and here is 3D. I can do the same. I can do the same. Volume of electronic state in 1D to K. It will be just this volume, 1D volume of all electronic space. I divide to K by this thing, and I'll get epsilon. I get energy root squared. It's number of states, and density of states I should divide by energy and by this thing, and I'll get 1 divided by E squared. And I can show it on the graph. You see, I can compare it. For 3D, we have such function. It will be proportional to square root of energy. For 2D, I have these steps, this ladder, this constant energy at some points. And for 1D, I see this peaks, these delta functions, because it should go somewhere to infinity when we approach to energy. So, and for quantum dot, it's very interesting case. For quantum dot, it's zero dimensions. We'll get this peaks. It will get just this peaks, just sum of the delta functions. So that's very basic information about electron gas density of states. Of course, in crystals, you have more complicated story. It's also possible to calculate the story, and it's possible to plot it. And today we'll plot density of states for graphene, and then in homework you will do it for some other materials. Okay, I third or first time recommend you this brilliant book by Roald Hoffman. And before I taught in mathematical way about density of states, and here is in some physics way. You see, I want to connect density of states to band structure. They are connected. They are tightly connected. What's the formula of number of states? Let's say I will call density of states DOS, density of states, and for some energy multiplied by dE. So it's number of states in some interval, in some energy interval from E to E plus dE. I can build this energy. Here is energy spectrum. How energy dependent on K, on this wave vector. It's just very simple band structure, parabolic band structure. But what we'll see for DOS? For DOS, we'll see some tools. You see. So each density of states shows all the states, they are somehow located on this band, because electron can be located only in these bands. It can have only energy, allowed energy for electrons, only this band structure. So it can't have, for this simple structure, it can't have another energy than this EK. So all electrons' energy should be on this parabola plot. And what we see for the density of states, we see that here we have almost flat band, and here we have almost flat band, and we see a lot of density of states, a lot of states. We have a lot of states here because it's flat. And here in the center of this parabola, we have the smallest number of states here. So when band structure plot goes up, and it fast goes up, so it has big derivative. We have the smallest number of states, and when it's flat, we have the biggest number of flats. And for this parabola state, we have such parabola for a number of states. In the edges, you have the most states, and in the center, you have the least states. And this is some this is some states between them, between these two extremes. And now I'll show you some examples from this book. Here is density of states for platinum H4. It's rather complicated picture. It's more complicated than our parabolas, but it also consists of parabolas. This parabola, but we have a lot of parabolas. Okay, and how we can imagine? Let's say we have this. This picture, and we want to estimate how density of states plot will look like. Let's start from below. I have this parabola. I had to have such picture of density of states, but this parabola, it is very flat. What does it mean? It means that I will have a lot of states in the edges, here a lot of states, and here in this edge I also see a lot of states, and in the center, in the middle, somewhere here, I should have the least number of states, but it's almost flat. This parabola is almost flat. That's why that this thing will be not so huge. So you have this huge DOS and this small thing in the center of it. Then I have another band here, and from this band I also can say that it's rather flat. That's why we have rather big number of states, and that's why this plot will be so high, so huge. And center, you see center here, in the place where parabola goes up with the highest derivative. Okay, more complicated case, this thing, Empire State Building, with these three bands. I can divide it by three parts. I can take this Z2, it's d orbital, Z2 d orbital. I can take it this parabola, and in the edges of parabola here I will see small peak, and here in this edge I also see small peak, this, and between them I'll see this parabola, this DOS parabola, with the lowest amount of states in the center of this parabola. So I'll see such thing. Then I have two more bands, XZ, YZ. It's also some the orbitals. It is rather flat, and I'll think that this peak and this peak will be connected to this state, to this bond. Between them, I will see some parabola here, and I have the last XY. It is almost flat. That's why I'll have very huge amount of states. So all the states, they will be located in this peak, and this part of this plot, it consists of three bands: wide band, then not so wide band, and very flat band. I hope it's clear how we can create this density of states plot from how can we estimate it from band structure. This peak, rather flat x squared minus y squared here, and very wide z band. So we can see only one of its edges here, and then it goes down. Then number of states goes down. This is how band structure and states are connected. You see, it is divided by 4 sigma bonding states, sigma strong bonding. P, it's some electrostatic not so strong states. It's anti-bonding P. We have the same principle. This state will create such small peak. So the lowest state will create a very small peak. Then we have two flat bands. It's two bands. They will create very, very huge peak because they are almost flat. This band is not so flat, so the 5 sigma peak will not be so huge. And here we see two bands. They will create such 2p anti-bonding state with a rather low amount of states, but it will be rather wide. So I hope the idea is clear. I have another example. It's even more complicated example. So we see a lot of bands. We see this low energy bands like minus 33 electron volts. They will create such peak. So it's rather hard to say what band create what states because they're mixed. Then we have huge amount of bands near minus 15 electron volts, and we have huge peak, rather complicated peak. then minus around -10. Here I can say something about, for example, I think that this lowest band, it will create this peak. I think that these flat bands, they will create this huge peak in the middle, and maybe and some small bands should create this thing, and so on. So I hope this idea should be rather easy. At algorithm, how we will calculate all the stuff. Today we get another branch of our algorithm tree. So this branch will go to DOS calculations, and then in few weeks we'll add Fermi energy calculation to this algorithm. We have worked with band structure calculation, so we had to make some relaxation or maybe convergence test plus relaxation to get the structure. Then we get the structure and we provide self-consistent calculation, step 2. Then we go to band structure calculation, step 3a. I had to make calculation along high symmetry path in Brilliant zone. And then I make some post-processing and get the band, get the plot. And now we have another way to calculate DOS. To calculate DOS, I had to make non-self-consistent calculation. So this is also non-self-consistent calculation, but it's along high symmetry path. But this non-self-consistent calculation, they will be almost the same as path 2, but with bigger number of components. I will explain why do we need it. Then post-processing, and then we should calculate, should make some what. So, and I propose you to launch a virtual machine, and we'll start with calculation. Okay, you should find this lab 6 folder, and you should find 4 folders inside. Oh, you have launched the virtual machine. Relaxation, self-consistent, DOS, and bands. I propose to make all the calculations in different folders. So relaxation. I propose to skip this this step for now because we have done it for graphite 2 weeks ago. So the thing we had to get from relax step is crystal structure. So crystal structure, which will be not strained with some internal forces. And we have it all here in self-consistent calculation. So here I just have this structure. We have created because it's graphite, and we have done it 2 or 3 weeks ago. And SCF relaxation step and SCF step are the same as we had in our laboratory 4, and then it looks like almost the same as we had in laboratory 5. Okay. Then we can go in 2 directions. One direction is band structure calculation. We have done it. We have already done it. And I propose to start with this thing to make these calculations. And then we will do some DOS calculations. So I propose to make first step is to launch SCF calculation, self-consistent. So this all, and then we had to take all this data to bands folder, because band calculation. So this step 3a it should be it's not self-consistent calculation, and it had to use some data. It had to use some electronic data from self-consistent calculation. Then I launch it. I go to this folder, to the folder bands, and then I launch it. And now we had to extract all our data bands X, graphite band 2. Oh, maybe I don't have this file graphite band 2. No, I have it. I have graphite bands 2, and it's over. From all the steps, I had to get this file, graphite band dat GNU. It's convenient to plot, and I plot it with this graphite plot script. So it's like Python. And we have this plot which we already have built it. So you see 8. You see this 8 high symmetry points, gamma mk gamma, l h a. So it's like one closed loop in the middle of brilliant zone, then another closed loop in the edge of brilliant zone. Then we have these 2 interesting points in k and h. H is the same point as k, but in the edge of brilliant zone, but it's in the middle of brilliant zone. So we have this 2 interesting points, and we have made some calculations for graphene, and we saw that all these things are also in graphene, but in a more interesting way, that it's not like here these bands they're not flat. You see that they're not linear, but for graphene they are linear, and it makes graphene so interesting, and it makes this the electrons velocity very high in graphene. Okay, and we have made it, and we will then we will in maybe in half an hour we will return to the calculation. And now we had to go we have go to another part, to DOS folder, and I'll explain you about the files. So we have done this 2, 3A, 4A, and 5 for bands. So it was really easy, because we just know how to do it. Now we are going to DOS, and first DOS step, it will be non-self-consistent calculations. So self-consistent calculation is a Computational loop. We start with some electronic density. It's all here in this electron part. We start with some electron density. Then we solve Computational equations, system of equations. Then we get new electronic density. Then we check the convergence threshold. And then if everything okay, we say that the calculation should stop. That's self-consistent calculation. Non-self-consistent calculation, it states that we make this loop only one time. We make this we make this Computational loop only one time, but with previously pre-calculated electron density, with electron density from this self-consistent calculation. That's why we copy all files from SCF folder to NSCF folder. And we have some difference in this file. First difference is calculation type, NSCF. So I just, it was SCF and it's NSCF. What our input says, input here, calculation types. SCF, we have used almost all of them already. So SCF, self-consistent type, non-self-consistent bands along some paths, relax, we didn't use relax, but we used VC relax. It means that we have allowed vectors and items to change. And here is molecular dynamics. We will not use it, but it's also a good thing to work with molecular dynamics. Okay. More differences we see here. Occupations. For our SCF step, it was like occupation smearing, and then we had two more options for occupation smearing, like Gaussian and the Gauss. I will say a few words to remember what is occupations here. It is used. You see, it has another color. Smearing is okay for almost all materials. It's rather a simple thing. It's very good for metals, but for non-metals, it also will have some reasonable. It will give some reasonable calculations. For this smearing, we have two options. For this occupation smearing, we have two options: smearing and the Gauss. Smearing can be some Gaussian spreading. We use it because we don't pretend to make very precise calculations. That's why we can neglect this Mensak-Faxton, Mazari-Vanderbilt. They're also okay. But Gaussian in most cases is okay, or Fermi-Dirac. And then we have some option, the Gauss. And I have told you what means the Gauss. It means that it's some smearing. Okay, smearing inside smearing. So we have all these electrons. They are located along these bands, and but these bands, they have 0 dimension because it's only line. It's only line. But electrons not just like line. So we have to make it more real, and that's why we have to smear in some way this energy. So we have to make these bands fatter than they are, because they're very thin, and we have to make them some fatter. That's why we should use the Gauss. For tetrahedron optimization method, for this nscf calculation, we should use another method. It calls tetrahedron method. It is very good to calculate the states. Why? Because you will see when we will get this file, you will see that the states, they are very low. I mean that it's like 2 multiplied by 10 in the power of -4. So it's very. It means like its probability of electron to be in some particular state, because we have a lot of states, we have very small probability. That's why the states are really low, and it's hard to calculate the states. That's why we had to use some advanced methods to get them. Just common Gaussian occupation will not be sufficient for this, and we use this tetrahedron opt. What's the idea? We take our brilliant zone and we divide it. We take brilliant zone, we take all these copoints inside this brilliant zone, and then we build, we take each 4 copoints and we build these tetrahedrons. So, for example, copoints 1, 3, 4, 1, 3, 5, 6, and we have this tetrahedron. Then we have another tetrahedron, and so on. 2, 3, 4, and here will be something 6, I think. So we divide it in these tetrahedrons, and we use just common tetrahedron integration method. I hope you are familiar with this method. It is rather it's rather widespread among calculation methods, among computer calculations methods, or how to integrate some space, or how to integrate some square, or some other things. So we had to use this. It means optimizations. These guys, Blochel, Jepsen, Anderson, they took some tetrahedron methods that made some mathematical stuff to make it fast, and very reliable, fast and reliable to calculate doses. So okay, of course we can use these occupations. We can use this method. I think this is the best method for occupation. But also, if you will use occupations with the Gauss and some other stuff, you will also get some doses. But the dose, they will be dependent on the Gauss. You see such things, yeah, such plots. For example, if we will have the Gauss too huge, we will not see most peaks. They will be smooth, all these peaks. If we have very low the Gauss, maybe we'll have too huge computational time. We will have a lot of peaks, yeah, it will be cool, but we'll have too huge computational time. And it's really hard to find some adequate level of the Gauss. We should make a lot of calculations to see, and then we should explain in our paper why we had used the Gauss and so on. So the Gauss it's problematic stuff, but tetrahedron opt gives us very good dose with good peaks, and we don't need to use the Gauss. And that's why I propose to use this method in all our next calculations to get those. And third difference, components. We had to have a lot of components. Why? Because the more components, the more precise this tetrahedron method, and the more resolution we will have in this plot. From some number of points, so it can be from my own experience. I have calculated titanium diselenite, and it was like in one key point grid. I get some stuff, some plot, but then I increased key point grid to a really huge number of key points. It was like 70, 70, 35 or something like this. And I'll get very, very long and short peak. I had very, very long and not wide peak, narrow, yeah. And I didn't get it with lower component density. So component density is also very important, because the more components you have, the better resolution of this plot you get. But computational cost hugely increases with number of components. So I think you have checked it when you made your convergence tests, that like components can twice, 10 times, 20 times increase this calculation cost. Okay, this is what I wanted to say about non-consistent step. So we needed to get good dose plot with good resolution. That's why we increase key points. That's why we use this advanced method tetrahedron. Because the Gauss stuff is really it's really crazy, because we had to do something with the Gauss. So nobody want to do it, but tetrahedron is okay. But for some systems, for some huge systems, tetrahedron method can be very slow, because it demanding in computational cost. Okay, and I propose to return to our lab. And what I can do, I also had to copy this SCF files to DOS, because here I have electronic density, which will be used in an SCF calculation. You see 3 plots. You get 3 different plots. 4 plots even today, because one plot we have already made. It was a band structure plot. I paste it, And now I can start the calculation. I go to this DOS folder. I started with the same PW. Graphite, nscf, nscf in, graphite, nscf out. And it will be a boring calculation which will last for maybe 2 minutes or 1.5 minutes. For some calculations, as our calculations, I mean that we want to get some DOS, but we don't pretend to get very cool DOS. We don't pretend to get the best DOS plot in the world. That's why I propose to take these points twice more than we have to an SF. In SF, it was like 884. Here, I just twice each of them. Of course, it's not enough for very good DOS, but it's enough for rather good DOS. And you'll see that it's okay. Okay, it was finished. It's okay. And now I had to make some additional post-processing step. You remember that we have used this dos.x module to extract all data in a useful format. Here we use dos.x module to do the same, to create DOS file, to create some text file, and then we can plot it. So it will be like dos.x graphite DOS in graphite DOS out, and it will take some time. And what about this file DOS in? It's very simple. Prefix, audir, name of file, and delta. So it's the main difference for bands. I can show you the same plot. Bands in. You see, they are almost the same. They are very simple. DOS here and bands here. Prefix audir fill band and fill DOS. And here we have delta. How do you think? What is delta? What should it make? Yeah, you're correct. Its energy step here. This is the E is like delta. So we have number of intervals. Each interval will be 0.01. Of course, we can make it very small. Then we'll increase some compression time. We'll increase number of density of states, and we'll get more precise plot. But okay, if you will get it too low, you will not see this beautiful plot, but you will see a lot of it will look like noise. So it's also not a good idea to make this step too small. 0.01, I think, is okay. You can play with it if you want. Okay, I got what I got. I got this DOS out file. It's not very interesting. You see, it's very optimized tetrahedron method. It's used and nothing. It's like 1 second. No, 1 minute and 1 second. It's very simple. And we have this file, and we will work with this file. Graphite DOS.dat. It's also rather simple. It shows here like first column. It will be energy, and you see that energy step 0.01, 12, 514, then 504, and so on. So, and we'll have a lot of these steps, really a lot. If you choose 0.001, you have much more steps. Then you have DOS. This so it is like number of states inside this interval, and you see it's rather low. It's like 0.27 on 10 in the power of, and divided by 10, and so on. It's rather low. And here you see integrated DOS, and we'll return to it in a few minutes. In integrated DOS. And we can use this script to build it. The script is rather simple. You just load the data, name of this file, graphite.dat. Then you take energy level, its first column, then DOS values, second column, you set Fermi energy, and then you just plot one line. And also I added some stuff like fill between, and you'll see what it is. So this is all this is all stuff for plotting this this graph, and here is how we extract the energy. And of course, from each energy, from energy levels, it's like this energy column, we should subtract Fermi energy, because we should I want to say that Fermi energy is some center of our plot. That's why I should subtract it. It was almost the same as for bets. And now I push it. Python.
Also, you can try just Python.
It should work? Okay. The 3.7 is like ugly, yeah? It was slightly ugly. You see, no model matplotlib. It don't work. Maybe I had to install this. I think it's rather beautiful. Yeah. We can remove this thing. It's only okay. Nice. Okay, we see this plot. We see that and here is Fermi energy 0. We see that some states under Fermi energy, and we see some states above Fermi energy. So at 0 Kelvin, all energy, all the states are filled with electrons, all the states. Then when some temperature rises, electrons can move here. They can move here, and they can fill these bands, fill these states. You see that here we see more states, but here we see this small, very small gap. If you will make very precise calculations, it should be like it should be like it should be like few dots which just touch this 0, like in Michelangelo picture where God and Adam touch each other. You see, we can. So this gap will be very, very small. If you will have very precise calculation, this will be like small parabola with the center of in Fermi energy, and that goes. Yeah, it's DOS state. And what another thing we can do? We can add some integrated DOS. What is integrated DOS? Integrated DOS is like its third column here, and it just sum of these DOSes. So we take all these DOSes, and then we just sum them and make some sum of sum of these DOSes. How do you think? If I will sum up all these DOS states, what I will get? 1. Your point is 1. What's your guess? Number of electrons. Vladislav, what's your guess? We have 3 stakes. 1, number of electrons. We'll have a number of states, and this number of states will be twice more than the number of electrons. And I'll show you it in integral dos. It's almost the same. I just added this third column, and then I divided it by 2 to get the number of electrons. Why we get twice the number of electrons? Because of different speeds. Because we do it here in this formula. We want to allow each electron to show itself, to make one spin or another spin, and not be forcibly have some particular spin. In graphite integral dos. And you'll see what is it. Graphite integral dos. Here is. Also, I added grid for some convenience. What I have here, I have this DOS stuff, but it's squeezed because it goes up. And here is 8. On Fermi level, we have exactly 8 electrons. So it means that if we will make this equal distribution, we'll get this 8 states. Okay, number of electrons, it's graphite. We have 4 carbon atoms. Each of them has 4 electrons, 4 valence electrons. That's why we have 16 valence electrons in our unit cell. And below this, when the temperature is 0, we have 8 states here, 8 states below Fermi level, and each of the states filled by 2 electrons. That's why we have 16 electrons below Fermi level. But if we will take all these electrons and proliferate it on all space, we'll see that it will be 8 electrons below energy, below Fermi energy, and 8 electrons above Fermi energy. So this stuff, all these states, if you will sum up them, it give us 8 electrons or 16 states. And here will be 16 electrons. So it's very, very precise. And this integral dos, it's rather useful when you want to estimate some number of electrons. For example, most of stuff, most of electronic stuff are made in this, are made close to Fermi level. So all this conductivity and superconductivity and some other interesting things, we had to do them near Fermi level. And it's really useful to see how many electrons can be used in this inside this Fermi level. We see that here is like 8 here and here. It means that here not so many, not so much states, and almost non-electrons. It's some part of electron are used here in conductivity. So it's because we have very, very low amount of stuff of state. For example, for superconductivity, maybe you heard about such things. For superconductivity, we had to have some gap at first, because we should have some energy gap to electrons to go from this Cooper pairs to some non-superconductivity state. gap, and maybe we'll see very huge and tall, very tall peaks near Fermi levels. So if we see tall peaks near Fermi level, it's some predictor of superconductivity. It can be some predictor. That guys, for example, that guys with LK99, they made some calculations. They told that we have narrow bands near that. Oh, maybe I can show you with from first laboratory work. It was like this. Not laboratory. First lecture. Was like first lecture. Yeah, here you see these guys. They showed this peak near Fermi level, and they say, okay, it should be like very flat band here at zero, at energy, at Fermi energy, and we have such peak. And these dos, they are for spin up and spin down. We also will make this stuff, but next semester, next term. For spin up and spin down. Now we just don't use it. Okay. It's crazy. Demographic pyramid. You mean this, yeah? Yeah, maybe you see now we have a really low number of children. Yeah. Okay. Let's go. Let's continue. And I want to make this. I want to make such plot, and we'll make it now, right now, to make such plot, combined plot, DOS and band structure. And we can do it with another plot, another script. You see, we used this graphite DOS just to calculate this DOS, just to make this plot. Graphite integral to add some integral DOS, and here is third script, graphite bands plus DOS, and I want to plot them on one plot. But for it work, I had to copy from bands. I had to copy this file. GNU, yeah. Few words about the script. I hope you easily be familiar with the script. But it's like yeah, it's slightly different because this DOS stuff, it took Fermi energy from NSF. In NSF we have Fermi energy like 72332. Yeah, and for bands we used Fermi energy from SCF. It's slightly different. So usually it's not a big deal. We can use from SCF or from non-SCF. From non-SCF, it's slightly more, you see, it's like, so the difference is not huge. You will not see the difference. From non-SCF, it's slightly more precise. But in most cases, it doesn't matter. Okay. Here is just name of atoms. I specify them. Then I set this Fermi energy. Then I set the high symmetry points. I have already done it. We have already done it together when worked with graphite band structure. Then set up energy limit. It means like from -10 to 10. I made it here, but not here, because we have two plots and we have the same energy limit. Because if I will, for example, if I will have not here, but for example, if I will have here energy limit -3, 3, and here will be -10, 10, it will be very ugly. So it's not the case. So this stuff which I propose to change. Yeah, and then here is just some function to build to extract data for DOS. It's some function to plot DOS. So it's the same. It's almost the same as our two previous plots. If we had one plot, we had one script for bands and one script for DOS, and here is some combination of them. So it's some function to extract data. It's some function to plot the DOS. It's almost the same as our DOS script. The same thing to plot the band structure. And here, maybe also for some another structure, you will have to change this thing, because it's like this path. It's like this letters in the path. And nothing else. You can also you can also play with these ratios. I choose 3:1, but you may make it as you wish and as you according to your view on beautiful. I can show it. Hope it will work. Yeah, it worked. You see how beautiful this plot is. I have combined this graphite band structure with DOS. And you see the same thing which I told you in the first part of our today's seminar. When we have not a lot of bands, for example, in the middle on the energy level, on Fermi energy level, we have a very small amount of doses, or maybe absent doses here. So this absence of doses in the center shows it says us that we have this touch things, this Dirac, quasi-Dirac points in graphite. Then we go, for example, you see this peak, yeah? If you will take a lot precise calculation, you will see that this peak will increase. And what makes this peak? This peak makes this flat bands. We have this flat bands and this flat bands. And that's why we have this peak. Yeah. For this peak, yeah, we have these flat bands. Here are four flat bands. So 1, 2, 3, 4, and they are degenerated. And we have this huge peak. That's why. Below these flat bands, from gamma to R, so it's like in that direction in our brilliant zone, we have such amount of doses, and so on. So you see how beautiful, you see in how logical and good way they are connected. And next times, next times we will plot doses for each orbitals and for each atoms. So it also will be interesting. And with it, we can say what orbitals, for example, play the most crucial role in conductivity, or what orbitals play some role in bonding the atoms. What orbitals will create some law, will create the law of conductive zone or higher amount of valence zone. So we can take a lot of information from such stuff. Maybe for today it's all. If you have some questions. I think you have seen a lot of such plots in some scientific papers. For example, from here. Yeah. And we will, when we work with spins, when we will add spins, we will make such plots, such hedgehog plots in each direction, in each point. Okay, if you don't have questions, I hope you got it. You got some new information, and I hope today, tomorrow, I will make some homework for you to next module, which will be in the beginning of December. Oh, thank you.